Okay, yeah, let's get started. Sorry to interrupt. Yeah, so we'll start with deep learning. But given what Gerard just talked about, the BPP transition and so on, I just wanted to say a few words about that and how it relates to the design of experiments in neuroscience. Because, you know, in neuroscience, we're recording many more neurons, and we can't do that many trials. So neuroscientists are asking, you know, what can I get if I record more neurons? I mean, how many trials do I need to take in order to, like, figure out what I need to figure out? And actually, it turns out the BPP transition provides guidance for that. And I'll show you the BPP transition in the brain of a monkey, all right? So even monkeys can do the BPP transition. So here's the basic idea, just to, again, repeat what Gerard said. You know, in the context of data analysis, let's say, just for simplicity, your data is Gaussian distributed. So there's some true covariance matrix, which I'm going to change the notation a little bit. But there's some signal-to-noise ratio. And then there's some axis, W transpose, where W is a unit vector, where there's some excess variance. And then there's just the identity variance matrix. So basically, your covariance ellipsoid is elongated in one direction, in the W direction, and otherwise it's not elongated. Okay, in all other directions perpendicular to W, the eigenvalues are 1. Okay, now, but you never have access to the true covariance matrix. You only have access to P samples, S mu, drawn from the Gaussian distribution with this true covariance matrix. So you can form the empirical covariance matrix, which is 1 over the number of trials. Let's say P is the number of trials, so mu goes from 1 to P. S mu transpose sum over mu, right? So this is the empirical covariance matrix. It's an estimate of the true covariance matrix. And you want to ask, is the leading eigenvector of this empirical covariance matrix close to the leading eigenvector of the true covariance matrix? Right? So geometrically, what this, and remember, we're in the high dimensional limit. So C is an n by n matrix. Okay? In the neuroscience context, this is the number of neurons you're simultaneously recording. And P is the number of repeats of the experiment. And so, you remember, P is order n, right? So it's not like we have many observations, so we can easily see the axis of elongation. You know, in 3 dimensions, we may sort of have 3 observations, right? So it's not obvious that we can see the axis of elongation in the high dimensional statistics limit. But it turns out that there is, as Gerard mentioned, a phase transition where if we let alpha equals P over n, it's the same measurement density that we discussed yesterday. Okay. Now we have these 2 parameters, right? The signal strength, and alpha. Okay. So in this 2-dimensional phase plane, there is a phase transition where if you look at the order parameter, let's say we compute the leading eigenvector of this W, of C empirical, and let's call it W hat, an estimate of W. If we look at the dot product between W hat and W, there's a phase transition. And this is the phase transition. I didn't have a slide prepared for this. I'm pulling this off some notes that I made. Here's the phase transition right here. So the left is the correlation between W hat and W. And so if you look at these axes, right, so this is the signal axis, and this is the ratio of the number of trials to number of neurons. And basically, if you're above some hyperbolic phase transition boundary, i.e. for a given SNR, if you have enough trials, then the empirical covariance matrix leading eigenvector acquires an overlap with the true covariance matrix leading eigenvector. But below that, you don't. And as the signal increases, the number of trials you need decreases. Okay? So there's this hyperbolic phase transition boundary. And now here's the nice thing again about neuroscience, is that the way the true covariance matrix was defined, this wasn't obvious, this is a unit vector, right? But in reality, every individual neuron's activity is order 1, right? So what's literally happening is if you rescale the activity, so the sum squared activity across neurons is now order 1, like a unit vector, then your effective SNR is order n, where n is the number of recorded neurons. So as we start to record more and more neurons in the brain, we can take fewer and fewer measurements because performance only depends on this, okay? So actually, we did the analysis on data drawn from a real brain, okay? So we're violating all the Gaussian assumptions. Data in the brain is not distributed in a Gaussian way. But luckily, there is some universality in these results in terms of universality in random matrix theory where, I mean, there's different distributions going on here. Like, well, anyways, we violate many of the distributional assumptions that we're making here. And let's see if I can find this slide directly. Yeah, here we go. Exactly. Oh, no, that's not what I wanted. That's also not what I wanted. Okay, let me not try to be smart about this. Okay, here we go. So we put in the numbers that you'd expect from neuroscience experiments, and we found this, in simulations, this kind of a phase transition where if this is the number of recorded neurons and this is the number of samples, this is how well you can recover both the dimensionality, the number of non-trivial principal components if you have multiple spikes, and also the overlap between the subspace spanned by the leading eigenvectors of the empirical covariance matrix and the leading eigenvectors of the true covariance matrix. Again, in a situation where you have multiple spikes. You can generalize all of this to multiple spikes. And then we looked at this in the brain. So everything has changed. We're now no longer doing PCA. We're doing a slightly different algorithm called Gaussian process factor analysis. It's real neural data, so you don't see the, we're not making the same distributional assumptions that are made there. And you do see this hyperbolic trade-off between, this is the number of trials that we take, and this is the number of neurons, and this is the inferred dimensionality of the subspace. So, the leading eigenvector, the successive eigenvectors of lower eigenvalue, by definition, have a smaller signal. So you'll need more data to see them. But as you take more data, either in terms of number of trials or number of neurons, you start seeing more and more dimensions that pop out of the noise, the Marcinko-Pasteur kind of C. And then the subspace overlap also, compared to what you get if you keep all the neurons in all the trials. So we compute the subspace that we got using fewer neurons and fewer trials to the subspace we got using all the neurons in all the trials. And you again see this kind of noisy hyperbolic phase transition boundary. Okay?
So here the delta is fixed.
Okay, so what's interesting is that the delta is actually increasing with m, right? That's the key issue. That's the key difference between the theoretical kind of problems we're studying, where we're trying to find the phase boundary between impossibility of recovery and actual recovery, and what's actually going on in experimental data, where people design their experiments so they will find what they're looking for, right? I mean, they do it intuitively, right? But this shows kind of a little bit more rigorously that so this is what I was saying, right? Delta's order n, where n is the number of neurons that are recorded. So delta is increasing with n, which means that if you record more neurons, you can commensurately reduce alpha. And that's, and alpha's, the number of, well, we haven't normalized by n here, but it's a number of trials. So you recover this kind of hyperbolic phase transition boundary that was kind of predicted by simulations, but now it's in real brain data. Okay, so this actually is kind of very surprising to neuroscientists, because it can tell them that they can trade off very different experimental resources, number of neurons versus recording time. Right? So people are working extremely hard to design multi-electrode arrays that can dramatically increase the number of neurons you can record. But you may not actually need that many neurons if the dimensionality of your data is low and your recordings can be stable over a decent amount of time. So anyways, I just wanted to kind of talk about that and show like a real connection between BPP and what's going on. Oh, by the way, I didn't even tell you where the data came from. This is data from the brain of a monkey while it's performing multiple reaches. It's from Krishna Shenoy's lab at Stanford. And you know, this analysis never had access to the reaches. It was just trying to find a low-dimensional subspace in which neural activity resided. And neural activity turns out to reside in approximately a 10-dimensional subspace, while the monkey's doing various reaches in 2 dimensions. And so we're trying to assess how well we can recover that subspace as a function of the number of neurons we record and the number of times we observe it. Okay? Yeah? The Eigen mouse. Oh, Bob Dutta's work? Yeah, it's a similar idea. I mean, that's also, I mean, that was a little bit more sophisticated than PCA. But yeah, so Bob Dutta looked at these, and Ryan Adams looked at these mice behavior. And they did high-resolution like imaging of mice as they're moving around. And they tried to segment mice behavior into, so they did a combination of clustering, cluster-dependent PCA, and so on and so forth. And they tried to kind of classify all the behaviors that a mouse can do while it's moving around. That's actually also super important because there's this famous phrase, nothing in biology makes sense except in the light of evolution. All right? There's a riff on that first came from Terry Sinowski, which is nothing in neuroscience makes sense except in the light of behavior. And behavior is extremely complicated, right? It's very hard to quantify what we actually do, right? And so that was actually a very nice piece of work where they really tried to quantify what a mice actually does. And then once you understand the output of the brain, you can work backwards to figure out how the brain generated it. Okay, yeah.
So for different trials, do you always use the monkey to perform the same behavior?
Yes. So they worked very hard to control the trial. So these are reaches to a particular direction. The monkey was rewarded it for doing it fast. And so it does these very fast ballistic repeated reaches. But actually, I mean, even if the monkey's doing different things on different trials, if the collective activity lives in a low-dimensional subspace, then this analysis applies. Right? Yeah? Oh, yeah, sorry. So 1 is good, right? So red is good, blue is bad. Why is red good? This measures the kind of the average canonical angles between the subspace that you get if you use less data to the subspace that you get if you have all the data available to you, right? So that overlap goes back as you increase the amount of data, as you'd expect. And the inferred dimensionality goes up as you increase the amount of data because of this sequence of BPP transitions, right? Each time alpha exceeds a threshold set by a particular delta associated with an eigenmode, you see that eigenmode. It pops out of the Marcinko-Pasteur C. So that means to see the eigenmodes that have smaller eigenvalue, you need a larger number of trials. Okay? Basically, let's say the true empirical covariance matrix has a fixed number of eigenvalues that are just here, right? Now, sorry, the true covariance matrix. Now, let's say you have the empirical covariance matrix. If you have very few trials, this is all cartoon picture. If you have very few trials, the Marcinko-Pasteur C will envelop the signal eigenvalues. As you increase the number of trials, you beat down the Marcinko-Pasteur C, and then maybe the biggest eigenvalue pops out, but the other 2 eigenvalues are hidden. As you take more data, you beat down the C further, and maybe the second one pops out. That's kind of the picture. It's a sequence of BPP transitions if you have multiple eigenvalues that are large in the true covariance matrix. Okay. Those pictures are not to scale, and the geometry is all wrong, but the idea is there. Okay, so Okay, I want to now move on to deep learning unless there's any other questions. I just wanted to, just because Gerard gives such a nice overview of that, I just wanted to show you an application of it to really designing experiments. Okay, so let's see. So now let's skip to, we did the tensor decomposition yesterday. Okay, so now we're going to go to deep learning, and I think there's lots of ways that physics can help deep learning, that deep learning can help neuroscience, that neuroscience can help deep learning. So this interplay between neuroscience, artificial intelligence, and statistical physics or complex systems analysis, I think, is a very fertile field. I'll give you a very biased set of vignettes from work that we've done. But first of all, how many of you have not heard about deep learning? You have to be under a rock, I guess, in order to not know about it. But just to get everyone on the same page. So basically, a lot of the competitions that are being done in machine learning are being won by these so-called deep neural networks, right? So what is a deep neural network? It's basically a sequence of cascaded functions where each neuron sort of linearly summates its inputs and then applies a nonlinearity. And there's different choices of nonlinearity. There's different ways of pooling the inputs. You could have translation invariant connectivity or convolutional connectivity. You could have dense connectivity. There's many, many architectural choices that could be made here. Okay, this is one example of an architectural choice that really had a strong improvement in a particular image classification task. So in this image classification task, it's a data set called ImageNet. You have about 1,000 classes of images. Here are some classes, like a leopard, a motor scooter, a container ship, a mite, and so on, right? The network is responsible for taking a pixel-based representation of the image, feeding it through all these nonlinear layers, and generating 1,000 outputs, right? And the idea is the outputs, neurons, are in one-to-one correspondence with the classes in the data set. And the unit with maximal activity is the network's guess for what the class is. Actually, the network spits out a probability distribution over all 1,000 classes, okay? So it gives you what it thinks is its probability that the particular image belongs to each of these 1,000 classes. So now you can show an image and you can literally read out the top 5 most likely classes that the network spits out. And as you can see, it does pretty well, right? It got all of these right. Its mistakes are kind of interesting. It thought this mushroom was an agaric. I actually don't know what an agaric is. It's a subset of mushrooms, okay. So it's kind of interesting. The data set has agarics in it. It's once you have 1,000 classes, you get some weird stuff in there. Here's a Dalmatian sitting in front of cherries, and Dalmatian was a bit higher, and then grapes. Grapes was the second one, and then elderberries, and it didn't quite figure out cherries, and so on. So it's doing sort of well, and you can also kind of turn on one output and figure out which training data points would make that output light up. So that's like asking the network, what do you think is an elephant, right? And these are all the things that it thinks are elephants. These are all the things that it thinks are flowers, and so on and so forth. Okay, so these, and there's a whole bunch of other stuff that people can do, not only in vision, but also in text processing. There are works that can convert images into textual description of images, like this is a boy looking at his birthday cake, if it sees a picture of that. So it's really quite amazing. There's all sorts of theoretical questions here, many of which are beyond our current reach. Okay. Yeah. Oh, sorry. I didn't even talk about training. Yeah. So how do they get the networks? So remember, we talked about the credit assignment problem, right? If you hit the tennis ball wrong, which one of your 10 to the 14th synapses screwed up? We do not know how the brain solves that problem. In machine learning, they solve the problem in a very simple way. It's actually kind of surprising that it works. But basically, they just take derivatives. So it is supervised learning. So when you train the network, you feed a particular input, and you feed the network the correct output. Okay? The network spits out a set of probabilities, and you could, for example, train the network using maximum likelihood. So you increase the probability of the correct class, and therefore decrease the probabilities of all the incorrect classes. That's what the network is trained to do. So then you have the log likelihood function at the output layer, and you just take derivatives of that log likelihood function with respect to the synaptic weights, okay, in all the previous layers. And so let's say, and so you're basically computing a susceptibility, right? If I wiggle a weight all the way down here, how does that change the log probabilities there, right? So of course, the susceptibility going from a weight change here to an output there is the product of susceptibilities from layer to layer. So in backpropagation, the computer scientists call that backpropagation when you take the error in the output and you propagate it back to the weight. But it's the same as the forward propagation that leads to the computation of a susceptibility. And so you get a product of Jacobian matrices, right? So for example, if I wiggle this weight here, how much do I change the activation there? That's one Jacobian. If I change the activation in one layer, how do I change it in the next layer? That's another Jacobian. And you take the product of those Jacobians, and that tells you if I change the weights in one layer, how do I change the output? And then you move the weights in such a way as to lower the error in the output. That's the training. Okay? Yep.
Can you give some sense of, okay, so you have many layers. I know probably in detail it's too much to explain, but why 5 layers is good versus 4 layers?
Yeah. It's all empirical. We're going to talk about a theory of the expressivity of deep networks. What can a deep network express that a shallow network cannot? I'm not sure that theory fully answers the question in situations where you actually have a task. But here they do it all empirically. It's really an engineering subject. It's a dangerous place for physicists to wander. They literally just play around with parameters. The way the culture of this field works is you have poor graduate students who are messing around with all the parameters, and then eventually something works, and they win a competition. Yeah. Yeah, a shallow one, I mean, there's different terminology, but shallow would be sort of one hidden layer or 0 hidden layers.
If you see who won some of these competitions recently, you say 4 graduates, and it could be a whole team.
Yeah, it could be a whole team, yeah.
And what used to be deep was 8 layers.
Yeah.
What is deep now could be 100.
Yeah. I'll show you how to train 1,000 using non-equilibrium thermodynamics.
I don't know if 100 is really better than 8, but they win marginally the competition with deeper things.
Yeah. It's really an awful culture. I mean, it's, well, depending on your perspective. I mean,
The layers look different. Means they're a different scheme for feedback?
There's no feedback in this network. It's all feed forward. The way that things are different involve sort of, I didn't want to get into all these details, but for images, what's really important is maintaining a convolutional map. So you have a certain filter, a linear filter, which is a linear summation of pixels over a local region, and you repeat that computation across the entire region. So now you have various architectural choices. How many times do I repeat it? How many things do I skip? How big are the filters? How many different filters do I use? Those are all different architectural choices, and they contribute to these blocks, the sizes of these blocks. Okay.
Is there a sense in which this is like RG, in the sense of its coarse graining?
There is a paper by David Schwab and Pankaj Mehta and company where they show in a very specific scenario that one type of deep learning is RG. But in RG, you're always coarse graining, so you're taking degrees of freedom, and many degrees of freedom, and replacing them with fewer degrees of freedom. That's one aspect of deep learning, but another major aspect of deep learning is expanding the representation. So going from a small number of pixels to many more features. So I think RG is a very, very special case of deep learning, and deep learning is much more than RG. Yeah. Okay, so that's the basic idea. So what are the things what are the mysteries of deep learning that might be amenable to theoretical analysis in the near term, if approximately? So do I have that? Okay, no. So one of the things is learning dynamics, right? You're optimizing many parameters. You know, how can you even train these networks, and can you come up with simple theory to speed up the learning? The error landscape of deep networks, what does it look like? This is still an open question. I mean, it's as you know, the p-spin landscape is already complicated. Can you have networks imagine things that they weren't asked to imagine? So creating generative models. So we'll talk about that using ideas from non-equilibrium thermodynamics. And then this question of expressivity, like why do we need depth? What can you do with a deep network that you cannot do with a shallow network? And then the big kahuna is generalization, right? The whole point of this thing is you have some training data, and you train it to spit the right answers out on your training data. But you want to use it on new data that the network has never seen before, okay? So that's called generalization. And these networks generalize really, really well, despite the fact that they have many, many parameters, sometimes many more parameters than data points. And so there's some very recent work kind of looking at ways that why that might be happening, but there's no theory really on that yet. And I don't have anything to say about that today, unfortunately. Although it may be related to the landscape of deep networks. And I'll tell you what people are thinking at the moment, but there's no proof of any of those facts. Okay, so let's start with a theory of the learning dynamics, okay? So, you know, oftentimes what you see is that the dynamics of learning in deep networks is very non-trivial. You have these plateaus, you know, if this is training time, you have these plateaus where the error's not going down for a while, and then suddenly it drops, and then there's another plateau, and suddenly it drops. So it's non-trivial learning dynamics. We'd like to ask, how does the training time scale with depth? How should the learning rate scale with depth? How do different weight initializations? So you have to choose the weights initially. You have to choose them to be something. How do you initialize those weights? And can you find weights that actually help speed up the learning? And we actually find some that correspond in the notion of physics to dynamic criticality, where the susceptibility is neither grow nor diverge, but even more than that. You preserve the geometry of the gradients. So let's talk about that. So now again, so this is a bit more mathematical. So roughly, for all intents and purposes, you can think of a deep network as a cascaded set of linear, nonlinear actions. So basically, you have the input, you multiply it by a matrix to get the inputs to the next layer of neurons. Then you apply a pointwise nonlinearity to each of the inputs. And then you do the same thing again and again, okay? So there's very little hope for a complete theory of the learning dynamics with arbitrary nonlinearities, okay? So my first sort of work in this field was actually motivated by some other results, but was, well, what if we just analyze the dynamics of linear networks? So we look at a linear network. Now, in terms of expressive capacity, this would be a disaster as a model, right? Because the composition of linear functions is linear. You don't get anything with depth. You don't gain anything with depth, except maybe some low-rank approximations if there's a bottleneck in the layers, right? However, the learning dynamics of these networks are highly non-trivial, okay? Because if you think about what the error is the desired output minus the actual output squared, if you're just doing squared error, right? But the actual output involves the products of all the weights. So it's of degree d in the weights. The product is of degree d in the weights. The error is then of degree 2d in the weights. So gradient descent dynamics would be of degree 2d minus 1. So it's a highly complex coupled nonlinear dynamical system, gradient descent on the weights, even in a deep linear network, okay? So, yeah, so I guess that's what I was saying. If you just actually work out the gradients, you get many, many powers of the weights on the right-hand side, okay? And actually, this captures a lot of the non-trivial learning dynamics that we see even in nonlinear networks. So even in deep linear networks, if you train them, you see these plateaus of high error and then sudden drops to low error. And actually, there's this interesting phenomenon where the thing that gave rise to deep learning, the first paper by Hinton on the subject, was that you could pre-train these networks in an unsupervised learning way. And then once you pre-train them, you can just do supervised learning, and you find that you can train it rapidly. This also holds for deep linear networks. If you take a deep linear network and you pre-train it, and let's say this is the pre-training time, and then you look at the learning curve of the network, it drops precipitously, right? Whereas if you don't pre-train it, it takes a long time to drop. So the very empirical phenomenon that started deep learning was actually present already in deep linear networks, suggesting that deep linear networks are potentially an interesting laboratory for understanding nonlinear learning dynamics, yeah?
The parallel and the sudden transitions are not linked to the decreasing learning rate, even with the constant learning rate.
Yeah, even with a constant learning rate. Actually, we worked out the theory with a constant learning rate. Yeah.
This is supervised learning in both cases.
Supervised learning in both cases. Same problem, yeah, in both cases. Yeah. This is actually MNIST on the linear network.
How is the pre-training done?
You do an autoencoder, so you try to you do this greedy stacked algorithm where basically, you have your inputs, you have your input vector, and you train a one hidden layer neural network to reconstruct your input vector. Okay, then you get that, and then you freeze it, and now you have new inputs, and you stack it again, and you try to do autoencoding. So you do this greedy layer-wise options. You never have to propagate across multiple layers. And then you get this initial deep network, and then you train it from there, right? So, that was like the earliest trick, because back then people didn't know how to train very deep networks because they didn't have the tricks that we do now in terms of initialization and momentum and all this kind of stuff. So that was like kind of the first trick that they did. Okay. So this is just to show you that what we're doing is not entirely insane. And actually, we're going to learn something that will help us train nonlinear networks. Yeah. Is there some what? Yeah, that's an interesting question. Right now, rectified linear units are very popular because, so these are units that look like this. Deep learning kind of started with 10H units that look like this. The thing with this is if you think about the susceptibilities, right, from input to output, you're going to have to take derivatives of the nonlinearity, right? So if I change the input, how do I change the output? That's just the derivative. And so what happens is the derivative is 0 in a lot of places, which means it doesn't allow you to backpropagate the gradients. For the ReLU unit, when it's active, the derivative is 1. So that, so that's why people use this. But we don't have a very good theory of how different nonlinearities impact learning speed.
Can you do worse than linear?
Huh?
Can you do either in the linear version of it does worse than linear?
I'm not sure. I mean, yeah, you could choose pathological nonlinearities that are just really bad and you can't train them. And then you could potentially do worse. I'm pretty sure I could find one where you do worse than linear. But if most of these reasonable ones do much better than linear because the fundamental tasks we want to solve are nonlinear, right? Is there a cat in this image versus a dog? That's a nonlinear operation on the pixels. Okay, so let's first analyze just the 3-layer learning dynamics. So basically, again, you can just like we did yesterday, you can go to continuous time and write down a set of differential equations. As promised, they're cubic in the weights because there's 2 layers of weights. So the learning dynamics is cubic in the weights. It's coupled and nonlinear. But you can actually find a really nice closed-form solution to these nonlinear differential equations. And again, it boils down to doing the singular value decomposition of your data. So basically, what's driving the learning dynamics is essentially the correlations between the input and the output. So that's the correlation matrix between activity in the first layer and activity in the output layer in the training data. And of course, the input correlations, we're going to assume that that's white. So we have whitened input, so the input correlations are the identity. So then everything, the statistics of the training data that's driving learning, just like in PCA, was the second-order statistics because the network is linear. Okay. So we have the training data. I should be a bit more explicit. Right. So I have the training data, x mu I, which is the activity of the ith neuron and the muth input. I have the desired output, y mu I, or y mu j, where this is in the output layer. And sigma 3,1 ij is just sum over mu, x mu I, y mu j. So this is saying, so if this is your 3-layer network, this is, index I is out here, index j is out there. This is saying, how does neuron I in the input correlate with neuron j in the output if I average over all the training examples, right? This is a property of the statistical, this is a statistical function of the data, okay? of course, that function of the data will seep into the weights of the neural network, and we'd like to understand exactly how it seeps into the weights. Right? So the way it seeps in is as follows. We can construct the singular value decomposition of the data. Okay? It turns out that if you truncate the singular value decomposition to a finite set of singular values, then that's the best, if you keep R singular values, that's the best rank R approximation to this entire matrix in the sense of mean squared error. Okay, so in some sense, truncating the singular value decomposition is like the best way to approximate the input-output correlation matrix. Okay, now here's the exact solution to the learning dynamics in terms of the statistical structure of the outputs. Okay, we can take the product of the weight matrices, okay, and we can actually express them as a time-dependent singular value decomposition, where the coefficients these coefficients are time-dependent, and they rise up like this in a sigmoidal fashion, and there's an exact solution to this, which is the sigmoid. And basically what happens is the different modes of the input-output correlation matrix in the training data are learned at different speeds, where the larger singular value is learned faster. Okay? So in fact, the sigmoidal transition occurs at a time that's 1 over the singular value. Okay? So weaker singular values get learned later, kind of like the BPP transition, where as you add more data, you see smaller singular values or eigenvalues of the covariance matrix later, right? But this is not related to the, I mean, it's spiritually related to the BPP transition, but it's different. It's an exact solution to a differential equation for a neural network learning, okay? Okay, so the basic take-home message that I think will generalize in other scenarios is that stronger statistical structure in your data is learned earlier. Okay? It just so happens that in this deep linear network, we know exactly what the statistical structure is, we know exactly how to quantify strength by singular value, and we know exactly how to quantify time by 1 over singular value. Okay? And so basically, this is what leads to these plateaus, right? The network is not learning something, and then suddenly it learns something, so the error will drop. Then it learns something else, so the error will drop again, and so on and so forth. What's actually going on in terms of the geometry of weight space, like why do you have these plateaus? It turns out that there are these hyperbolas that in weight space that correspond to 0 error, and so the network dynamics will go there, but there are also unstable saddle points in weight space that attract and repulse the dynamics. There's a stable manifold here that attracts the dynamics. There's an unstable manifold that repulses the dynamics. And so a generic learning trajectory will get attracted through the stable manifold and then repulsed to the through the unstable manifold and end up at the space of 0 error. Okay? And what's going on while nothing is happening is that you're being attracted to the unstable fixed point. And then you rapidly get repulsed, and that's the rapid rise in learning the mode. Okay, so these saddle points are appearing all over the place in the learning dynamics of these linear.
Going down slower than going up. Going in slower than going out.
That has to do with the weight initializations. If you initialize the weights to be small, then it takes some time to escape the saddle point. So you can initialize the weights to be large and avoid that. And I'll show you how to do that soon. Yeah?
So if you analyze some classical algorithm for just PCA,
Yeah.
you get the same result?
You don't, because PCA is done by power iteration, right? It's done in a very different way.
Yeah, but in power iteration, you first get the large eigenvalues. And
Oh, that's
then
true,
you
yeah.
iterate on them to get the lower.
Yeah, it's true. Okay, so, yeah, so what happens is in power iteration, the largest eigenvalue dominates and you lose all the others. Then you literally have to project it out and do power iteration in the orthogonal subspace. So it's a very different dynamics, right? Here, gradient descent is learning all of them all at once. It just so happens that the first one gets learned first. But then you don't have to project it out. The rest of the network will keep learning the rest of it, right?
I think that like subsets of power iteration is like the off-the-shelf thing, but if you say, take some of the like alternating minimizations that people would use, maybe not for PCA, but for some like constraints
Yeah.
PCA, that's more of that's more similar perhaps to gradient descent.
Potentially, yeah.
And that for matrix factorization that resembles
Yeah.
more gradient descent, it could probably be something.
Maybe, yeah. Yeah, it might be true. I haven't really thought about the dynamics of alternating minimization, just because that doesn't generalize to multiple layers. Well, I mean, it could actually, but there are other algorithms that involve alternating minimization, where you fix some set of weights and minimize over the others, and then fix the others and minimize over the rest. We just haven't thought about those dynamics. I don't know. I don't really know the answer. We're kind of analyzing the dynamics that everybody uses, which is gradient descent in the deep learning world. I'm not sure why they don't use alternating minimization for networks of like 100 layers or something like that.
But they don't really use gradient descent. They use stochastic.
Yeah, exactly. They use stochastic. Yeah, so actually very important. We're analyzing batch gradient descent, where you take the entire training data set and you compute the gradient averaged over the entire training data set. Because the training data sets are so large, they do this over subsets of the training data set, so each step is a noisy estimate of the full gradient, and that actually helps with generalization, because adding noise can help regularize a little bit. There's so much to talk about. Like, let's try to keep going. Okay, but what can this analysis teach us, maybe even in a practical sense, about how to train nonlinear deep networks better? Okay. So why is it that training nonlinear deep networks can be hard? Okay. So remember, I said the method for backpropagating, like if you have an error in the output, how do you figure out how to change the weights? Well, you compute a susceptibility, which is if I change this weights, how does the output change? Okay. That's the product of a bunch of Jacobians, so it's a product of matrices. Okay. So you have to think about products of matrices. Now there's a problem. If the matrices all roughly have small elements, then the singular values of the matrices will be small. And then when you take products, you'll get this exponential decay in the singular value distribution of the product. Okay? That's called a vanishing gradient. Okay? On the other hand, if the weights are too large, right, then the singular values of any one Jacobian will be bigger than 1. And then when you take the products, typically what will happen is the singular values of the product matrix, the product of Jacobians, will exponentially explode. That's called exploding gradients, right? So the very signal that tells you how to change the weights could either vanish or explode, okay? This smacks of dynamical criticality, where what you really want to be is you want to be in a situation where you scale the weights so that the susceptibilities neither exponentially explode or exponentially decay, okay? So that idea was kind of brought out in deep learning, but let's actually let's explore that idea a little bit more carefully. Okay, so let's analyze it in deep neural networks. Okay, but let's say they're linear. So let's say you just have a chain of weights. Okay, and you can write down explicitly the dynamics on weight space. If you have a linear chain of weights, you can solve it. You can get exact solutions. And let me tell you the big surprise that emerged out of this exact analysis. Okay? The surprise is the following. Again, this is all published, so you can look at the details. But you can choose a set of initial conditions, right, where all of these weights are close to 1. Okay? So you're kind of dynamically critical, okay? And in that case, what happens is it makes a striking prediction, is that the norm of the gradient will be order n. The learning rate that you take a step in the direction of the gradient, but you have a proportionality factor, which is your learning rate. You make that small. That's 1 over the depth. And then you can get a learning time that's order 1 independent of the depth. Okay? Now, what do I actually mean by learning time? I mean learning time measured in number of gradient evaluations. Okay? Of course, if you train a deep network, the time it takes to compute 1 gradient or 1 direction in weight space you should move, that grows linearly with depth. Right? You can't circumvent that. But you might think that there's a more adverse scaling where the number of times, the number of steps that you have to take, gradient steps that you have to take, may grow with the depth. Okay? That is indeed true if you initialize the weights badly, but if you initialize them at criticality, it turns out you don't have that extra adverse scaling in these deep linear networks. Okay? So this was a surprising prediction, so we tested it. We trained deep linear networks on MNIST. This is this famous digits task. You just have to tell from pixels what digit it is.
Is it easy to find those critical initial conditions?
Yeah, I'll show you how. There's a random construction that gets you there. Yeah. Basically, what you do is I'll go through it. It relates to products of random matrices, which is very cool, and properties of them. So, but let's just say we have these quote-unquote dynamically critical initial conditions, and we initialize there. This tells you, and then we do gradient descent, and then this tells, and you optimize the learning rate for each depth. So you choose the learning rate to be proportional to 1 over depth. And then you calculate the number of gradient evaluations, or number of epochs, at which the error falls below a threshold. So that's basically a measure of how long it took you to get to some good level of error, or some small level of error. Okay? Then what we find is we indeed find that as the depth gets very, very large, the learning time saturates. Okay? For this dynamically critical initialization. Okay, now the question is, how do you find these? Okay, so it turns out pre-training, the thing that I mentioned, does actually find these. And random orthogonal networks, where the W's are random orthogonal matrices, the columns are perpendicular to each other, also can find these special initial conditions that allow depth-independent training times. But if you just have random Gaussian matrices where the matrix elements are IID Gaussian, but you scale them so gradients neither explode nor vanish, cannot find them. Okay? So this was the next best method of initialization that was in the field. And so let me just show you that. So this is orthogonal weights, and you see depth-independent training times. This is the random Gaussian. It was Gloro and Benju who came up with this. This is random Gaussian, and you see that the training time grows linearly with depth. So it's a qualitatively distinct scaling. Okay? Now, why do orthogonal networks behave very different from Gaussian networks? To understand that, you have to think about the theory of products of random matrices. Okay? So let's think about a random Gaussian matrix, okay? And let's think about its singular values, right? The singular values determine how much the matrix scales up and down its inputs after one step of multiplication, right? So for a random Gaussian network, it's this famous Marchenko-Pasteur distribution when alpha equals 1. Okay, but that's one random Gaussian matrix, okay? Let's say you take a product of 5 of them. This is what the singular value distribution becomes. There are works that give you analytical formulas for the singular value distribution. And then you take 100 of them, and you get this very anisotropic distribution. Okay? If you compute trace W transpose W squared, or i.e. the average singular value, it will be 1. Right? So that means, on average, if you propagate a random vector through this product of matrices, its length will an expected value will be 1. An expected value over the choice of the random vector, and also over the choice of the random matrix product. However, it preserves the length of the vector in an extremely anisotropic way, because there's a bunch of singular values that are large and many, many that are small. So the way that it preserves length is it takes a vector, projects it onto a low-dimensional space, and then amplifies in that space. That's a horrible way to convey information about errors in the output back to the input. Okay? It's a very anisotropic way to do it. Okay? But what do products of orthogonal matrices do? So orthogonal matrices only rotate space without scaling it up or down. So every singular value of an orthogonal matrix is exactly 1. Furthermore, products of orthogonal matrices remain orthogonal. So obviously, the product of orthogonal matrices, every singular value will be exactly 1, right? So you don't get this anisotropy in products of orthogonal matrices, okay? So, you know, we all know that preserving the norm of a vector is not the same thing as preserving angles between all pairs of vectors, right? Orthogonal matrices do the latter, but scaled random Gaussian matrices do not do the latter. Okay? So we call this kind of dynamical isometry. As two error signals propagate through the network, they propagate while maintaining their angle and maintaining their length for the orthogonal case. Okay? Now, the immediate objection you're going to have is, oh, that's all fine and well for linear networks, but if you have a nonlinearity, it might destroy the situation. Okay? Why might it destroy the situation? Because now the Jacobian from the input to the output is not just simply going to be the product of weight matrices. I have nonlinearities intervening. These nonlinearities contribute an extra term to the Jacobian in the product, which is just a diagonal matrix with a derivative of the nonlinearities on the diagonal. Okay? So now we have to think about matrix ensembles where you have an orthogonal matrix and then a diagonal matrix, then an orthogonal matrix and a diagonal matrix, and so on and so forth. So that's where I'm going free. Yeah, free probability. Don't worry, I'm not going free in any other way at the moment. But so first we looked at it numerically, right? So again, of course, I scale. I have a scale factor here, right, for the orthogonal matrix. I'm going to call it G. Okay, and as long as the average slope of my nonlinearity is 1, there's sort of a dynamical critical transition where if G is bigger than 1, then everything scales up and I get exponential explosion in the singular values. If G is less than 1, I get exponential suppression. The critical issue is what does, no pun intended, is what happens when G equals 1. Okay, and of course, when G equals 1, the length of a random vector propagating through the network will be preserved. It will remain 1. But what we care about is kind of the worst case vector and the two extreme vectors. The one that gets most annihilated by the network, that's the minimum singular value of the product. And the vector that gets most amplified by the network, that's the maximum singular value of the product. So we care about the entire singular value distribution. So here you do see when G is less than 1, you do see the exponential decay. When G is bigger than 1, you see the exponential explosion, although it's a little bit weaker. When G equals 1, you can take the depth to infinity and you get a singular value distribution that remains within a range that's order 1. Okay? So this notion of dynamical isometry that we obviously proved for linear networks survives for nonlinear networks. Okay? And I don't have slides for this because this is the paper that's currently under review at NIPS. But what we've done since then, and this is work with some folks at Google, Jeff Pennington and Sam Schoenholz. Jeff's another string theorist, so it's super, and Sam's another condensed matter theorist. So we formed a little physics team at Google. And we've used free probability theory to actually compute analytically the singular value distribution. We've confirmed that as the depth goes to infinity, the singular value distribution stabilizes to a stable distribution. Okay, there's some order of limits that I'm going to gloss over at the moment, but basically, but in simulations we've kind of confirmed it where the networks are a size 1,000 and the depth is order 100, right? So we're kind of working in the order of limits where we take the weight matrix to infinity first, so we can apply free probability theory, and then we iterate it multiple times and show that it stabilizes. Okay, so that's all well and good, but does this help you train nonlinear neural networks better? And it turns out it does. Yeah? Is it? It's not the Wigner semicircle, actually. It's a singular value distribution associated with this random matrix ensemble that's products of orthogonal matrices and diagonal matrices with a particular distribution that happens to be a Gaussian fed through the 10H. Yeah?
How does the matrix, W matrix look like after the training is finished?
Excellent question. We only initialize the networks using this random construction. And it turns out as they train, they're obviously going to become different. But they retain for quite a long time during the training this nature of dynamical isometry where the singular value distribution remains within a range that's order 1. Then eventually it's going to kill some singular values associated with stuff in the directions in the input that you don't care about. And it'll amplify some other singular values associated with directions in the input that you do care about. So ultimately, the weights, of course, become correlated with the training data in ways that we don't really understand, except in the deep linear case.
So this is
Yeah?
for
It's all for pre-training, yeah.
These orthogonal matrices are not there in the matrix in the training range.
No, yeah, it's all for pre-training, yeah, exactly. But what we find is that if you pre-train this way as opposed to any other way, the learning curve drops faster during training.
Training, in mathematical terms, if I understand, is to put them in generic positions, so that, because that's what the free.
It's to put them in, not really generic position, because it's a highly non-generic initial condition. It's to faithfully propagate error signals in an isometric way, right? So that if you have two error signals, and they propagate through the network backwards, they both preserve their length and their angle. So error information is faithfully propagated, and these are all words, intuition, that I don't know if you should take me seriously. What we think is going on is that if you do propagate the error information faithfully, then you can make learning faster. Okay?
So the only thing you keep from the network are the dimensions?
Yeah, the dimensions, yeah. Yeah. Yeah? Sorry, yeah, I mixed up words. This is a random initialization. It's just random initialization, yeah. Pre-training has a similar effect because pre-training creates an autoencoder, right? If you have an autoencoder to begin with, then you're faithfully propagating information through the network. The problem is pre-training takes work. Random initialization doesn't. Yeah. Yeah, no, I did misspeak there. Okay. What time is it? Okay, so what we find, and this we don't understand, but it turns out that if you initialize with this dynamic isometry, you actually improve your generalization error. But we haven't really talked about generalization error yet. All we've talked about is descending the error landscape in a good way, or at least getting to a good point on the error landscape such that you can go downhill in a reasonable way. Okay. But we have more simulation results on other tasks which I'm not showing you here, which show that if you do this dynamical initialization using orthogonal networks versus Gaussian initializations, you do better. Okay. All right, so just to summarize the first part, deep linear nets like non-trivial, non-linear learning dynamics that we can understand analytically. The learning time is inversely proportional to the strength of input-output correlations. With the right initial weight conditions, the number of training epochs can remain finite as the depth goes to infinity for the linear networks. And you can speed up learning for these initializations for nonlinear networks. So these dynamically critical we call this, there's some terminology called the edge of chaos, right? But if the weights are larger and you have these nonlinears, you get chaotic weight dynamics, which we're going to discuss soon. So this critical point is like this edge of chaos. You get these depth-independent learning times. Okay, so now okay, so let's. It's not so bad actually. Okay, the next two stories are a little bit shorter. Okay, so the error landscape of neural networks, and this will tie in, though not in as a detailed way, but in a qualitative way, to what Gerard was talking about in terms of the error landscape of P-spin models and also just Bray and Dean, the random landscapes. So, this is now obvious to us, actually, but it wasn't so obvious to the deep learning field. That it was often thought that local minima at high error stand as a major impediment to non-convex optimization. And the reason that was such a prevalent idea, perhaps in the optimization community, is if you just draw a random error landscape over a low-dimensional space, you could indeed have many local minima at high error, right? This is a cartoon of a protein folding funnel landscape. But now of course, that in random non-convex error surfaces over high-dimensional spaces, local minima at very high error relative to the global minimum are actually exponentially rare in the dimensionality, right? Instead, you get a proliferation of saddle points at high error. And we actually developed an algorithm that can rapidly escape these saddle points in high-dimensional spaces. So this was work that we did in this paper. There's, of course, very closely related work done by Anna Kromanska working with Gerard and Jan LeCun and company. But they both have a similar story. Okay. So we didn't try to approximate the loss landscape of deep neural networks at all. We instead tried to rely on universality in the following sense. So we asked, like, what does just a generic landscape look like? So generic landscape is you have a domain, and you have a the error at point x is a Gaussian random function. The error, or E of x, is a Gaussian random function such that if I evaluate E of x and E of y and I take the correlation, let's say there's zero mean, then this falls off as some function of x minus y, right? For the p-spin model, I think it's the distance to the pth power. I think Bray and Dean looked at e to the minus x minus y over some length scale, if I remember correctly. There is a square, yeah. So the basic take-home message is now you can take every critical point and plot it in a two-dimensional feature space, where the two-dimensional feature space is how high is the critical point, and what is the fraction of negative eigenvalues of the Hessian, right? That's like the index. Well, it's not the index, but the fraction of negative eigenvalues of the Hessian. That's the feature that we choose. And so Bray and Dean kind of did that using the Cauchy-Rice formula and all that kind of stuff. And the basic take-home message is that these you get the complexity of these critical points is large everywhere. But if you fix, for example, the index, and you ask what is the most likely configuration of the energy, or vice versa, it turns out that the critical points concentrate on a monotonically increasing curve. Okay? There's some subtleties associated with the minima and the width of the band of minima and so on, which I'm going to gloss over. But Girard did a very beautiful job of looking at it in the p-spin model. But the basic idea is the local minima sit, of course, at low error, and they have zero negative eigenvalues of the Hessian. The maxima sit up here at high error, and all eigenvalues are 1. But as you go higher and higher up in energy, you develop more and more negative curvature directions. Okay? So, and this is very intuitive, right? If you just have a very generic landscape, what are the chances that at a generic critical point intermediate between the minimum and the maximum, all directions curve up, right, corresponding to local minimum? The answer is exponentially rare in the dimensionality. It's just like having an eigenvalue distribution of the random matrix associated with the Hessian suddenly shifting all the way to the other side, So that's exponentially rare in the dimensionality. That's the large deviation principle. And so generically, you'll have as many directions going up as down, unless you're already near the bottom, in which case there's nowhere to go but up. Or unless you're already near the top, in which case there's nowhere to go but down. Okay, so as physicists, we're used to the idea of universality, right? There are certain questions whose answers don't depend on the details of the physical system at hand. They may depend really only in the dimensionality or symmetry of the order parameters involved. And so maybe this is the picture for deep neural networks. Okay? Of course, computer scientists are very different from us. They think everything they're doing is very special and nothing's universal, right? So they might say, oh, no, that's a random landscape. We're looking at deep neural networks. It's very, very different. So anyway, I teamed up with Yoshio Bengio, who has an army of graduate students who are very good at training these things. And these are the same graduate students who are tuning hyperparameters all the time. They're very good at doing that. But what we did was we decided to test specifically this. I suggested, why don't we plot this for these deep neural networks and just see what it looks like? Okay. So how do we find saddle points of critical of different indices just numerically? Okay. Well, we just did a very naive method, which is let's just use Newton's method to find saddle points of any index. I'll discuss Newton's method soon because I'm going to discuss a modification of it that escapes saddle points. But it turns out Newton's method gets attracted to saddle points of any index. Okay, I'll explain why in a little bit. I'll define Newton's method in a little bit. And so now again, we don't know if Newton's method does an unbiased kind of survey of all the saddle points. So all we can do is we can just report what Newton's method found. And what it found was exactly qualitatively what was predicted by the Bray and Dean landscape picture, which is, so this is the index of the critical point, fraction of negative eigenvalues, and this is the training error. And you see this monotonically increasing curve, both for a deep neural network trained on MNIST and a deep neural network trained on CFAR10. CFAR10 is an image classification task where you just have 10 classes, and these are more complex images than just digits. Okay?
And I question, I mean, why, I understand that Newton method gets attractive by samples, but the gradient descent that you talked about in the first part doesn't, right? So
Yeah.
hear about why
Oh, because I specifically wanted to survey the saddle points, right? I wanted to test this picture. So I care about critical points of all indices.
Okay, but
Yeah.
you talk about improving the method, whereas we have the gradient descent that does avoid them.
Oh, it does better than gradient descent. Oh, sorry. I improved not only over Newton, but also gradient descent. Yeah. Okay, so again, this should be taken with a grain of salt, right? Obviously, deep neural networks are not exactly like random landscapes, but at least to the extent that these numerical experiments make them look a little bit like them, right? And again, it's kind of obvious. What holds, the intuition that holds for random landscapes should hold for any high-dimensional optimization problem, any generic enough high-dimensional optimization problem. If you're at high error, chances are there are as many ways to go down as there are to go up at a critical point, right? Okay, so what can we do about this? So first, what is Newton's method, and why does it get attracted to saddle points? And how might we get an algorithm that's better than actually gradient descent even, which doesn't get attracted to saddle points? So Newton's method, what it does is you take a gradient descent step, but you pre-multiply by the inverse Hessian. Okay, now why do you do that? The entire theoretical motivation for Newton's method is that you descend a quadratic bowl in one step, right? So if you have a quadratic bowl and you're here, if you apply that update, you will end up at the minimum in one step, okay? The reason it's kind of useful is if I look at the kind of the contours of this quadratic bowl, and if it's an ill-conditioned problem where some of the eigenvalues of the Hessian are large and other ones are small, right, then dividing by the eigenvalues of the Hessian in each of these dimensions will, in this direction, the eigenvalue is small because the contour is wide, and in this direction, the eigenvalue is large. So this is a large eigenvalue. I'll just call it lambda large. And this is a small eigenvalue, lambda small. So clearly, to get to the minimum in one step, you have to go a large distance. So you want to divide by the small eigenvalue. And here, you don't want to go a large distance because your curvature is very large. So you divide by the large eigenvalue. Okay? In both cases, you divide by the curvature, and that corrects for the ill conditioning. Okay? However, what if there's a negative eigenvalue? That gives you an extra minus sign and turns you uphill. Right? So if you're on a saddle point, if you're up there, yeah, you'll go down. But if you're down here, you'll go up because the negative curvature gives you that extra minus sign. That's why Newton's method gets attracted to saddle points. So one kludgy fix is just to divide by the absolute value of the Hessian, okay, which is by definition a matrix with the same eigenvectors, but the eigenvalues have been replaced by the absolute value. That solves the sign problem. It gets rapidly repelled by saddle points. But there's a more general derivation of this optimization, which is you basically minimize a linear approximation to the function. But if that's all you did, you'd go off to infinity. But you do it within a trust region in which the linear and the quadratic approximations agree. So that sets a boundary. As soon as my linear and quadratic disagree, then I don't go any further. But within that range, I use the linear approximation. If you work out what that kind of dynamics does, it yields approximately this learning algorithm. Okay? Again, all the details are in the paper. Okay?
So that's a second order method, right?
It's a second order method. To get it to scale up, you really have to marry it with approximate second order methods, which has not been done yet. That's an interesting research direction. It's not a direction that we're going because we're interested in other things. But, yeah.
To use it in practice, you have to do one of the things that they do in BW, FGS
LBFGS, yeah, exactly, exactly. What you want to do is you want to maintain a low-dimensional subspace determined by the history of gradients, compute the Hessian in that subspace, and only in that subspace, and then do the absolute value in that subspace. That's actually a very interesting direction for future research.
You know, when you talk to you talk with Benjo,
Yeah, yeah.
There, the idea of going to second order is like.
I think it's.
And even computing a gradient is too hard. They don't do that. They can only compute the gradient in one direction.
Yeah, I agree. I was going to actually discuss all of this stuff. I don't think this is the final solution exactly for the issues that were just raised, and I was going to raise very, very soon. It's just an interesting, potentially scientific way to explore the landscape, because we learn more about the landscape by exploring it using very different dynamics, right? So I'll tell you, I'll show you what happened actually. Let me skip this slide, it's a detail. But so what we did was we first explored the landscape using SGD, right? And then what happened is the error fell into some plateau like this, okay? Now, because the error fell into a plateau, you might think that you're kind of at a local minimum, right? But if you switch to, we call it saddle-free Newton method, if you switch, you find that the error suddenly goes down, both for a deep autoencoder problem and even a recurrent neural network trained to solve a sequence prediction task, right? So here's the same thing. You have a plateau, then you switch to saddle-free Newton, and it also drops. Now, this is not shown here, but we monitored the eigenvalue. And oh, by the way, we did this on relatively small problems with about 1,000 to 3,000 weights, where we could exactly compute the Hessian and invert it with no approximations, okay? So now, what's not shown here is that we also monitored, and by we I mean Benjio's grad students, they monitored the eigenvalues of the Hessian, right, along the trajectory. Now, this is no longer at a critical point because you're going along the optimization trajectory. And when you dropped here, the number of negative eigenvalues went up, okay? So that suggests a picture that this plateau is not really a local minimum, but it's actually a saddle point, and you're kind of getting slowed down because of the flat directions, right? So remember, in the picture that the Kac-Reitz formula gives you, right, it kind of tells you the entire spectrum of the Hessian. It's like a Wigner semicircle shifted by the error by an amount determined by the error level. So you have a finite density of directions that are kind of a zero eigenvalue, right? But a zero eigenvalue corresponds to a very shallow landscape, right? So you kind of have these many flat directions, and what seems to be happening is that saddle-free Newton is exploiting or is dividing by the small eigenvalue associated with flat directions to rapidly escape the saddle point, okay? So second-order information, when you can compute it and use it, it does help. But I completely agree, it's not a solution to the problem of deep learning, because what people are doing now is using millions of weights. And you cannot compute Hessians in a million, because you have to compute a million by million matrix and then invert. It's just not feasible. And you have to do it multiple times.
The shape of the Hessian, when you explore them?
Yes, we actually, that was, did I have that? Yeah, that's here. Yes, we actually looked at the eigenvalue spectrum of the Hessian. And it doesn't, of course, it doesn't look like a semicircular law. We're never expecting that. We were only really expecting this thing. There's a predominance of flat directions. The reason I think that's happening is that the data live in a low-dimensional space, so that if you think about how the data constrains the weights, it doesn't constrain the weights in all possible dimensions in weight space. So therefore, there are many flat directions in weight space. But again, those flat directions don't matter, because those are directions that are unconstrained by the data anyways. However, they might matter for generalization, because one thing you have to realize is when you're training neural networks, you're always solving the wrong problem. You're minimizing the training error, but what you want to minimize is the generalization error, which is what you would have if you had access to infinite data. So if your finite data set is unconstraining the weights in directions that an infinite data set would care about, then you're in trouble. But I suspect that's not the case. It's too much. Okay. So anyway, this is the spectrum. Good luck coming up with a theory of it, right? It's
The blue thing is the spectrum. Where do I see this shape of the spectrum?
this is the spectrum at different error levels, right? So this is how the spectrum, this is exactly the data you'd love to see, right? How does the spectrum change as you go down in error along the optimization trajectory? And again, we only did, I think, 1,000 weights here, so we don't have that much information, you know, but so it's not, we're not at the, like, of course, with 1,000 weights, you see the Wigner semicircle in random Gaussian matrix because everything's self-averaging. It's not at all clear that things are self-averaging in this situation, right? So anyway, it is what it is. I think there's much more room to do larger network. I mean, we would need Google scale resources, but we have access to them.
Something, it's a real Hessian coming from one of those.
Yeah. It's a real thing. Yeah. Yeah.
Observation about the number of negative directions dropping when at the point where the training
Increasing. Or sorry, the negative eigenvalues get larger. Yeah.
Okay.
As you.
Specific to this setting period matter, or would that also happen if you just train with randomness?
That's a good question. I don't remember. We looked into that. I don't remember the answer to that. Yeah. The problem, I guess, with training with stochastic gradient descent, where did it? Is that you just get stuck in this plateau and you never escape it, right? So it's only when you switch to saddle-free Newton that you see a change in anything at all. And the change that you see is that the negative eigenvalues become more prominent along the trajectory, right? But by the way, these are all things we could do in the p-spin spherical spin glass, right? I mean, we could try it. Yeah, we switched algorithms. Yeah.
Because earlier in the lecture you were saying also for the just classical like propagation that you observe these like plateaus in the training
Yeah.
and suddenly
Oh, yeah. Yeah, that we do understand. At least in the linear network, it was exactly this. It was being repulsed by a saddle point.
right, but if
Yeah.
you look at the Hessian along the way,
Yeah. I think you would because the error landscape is quartic in the weights, the Hessian will be changing. And I think the curvature is more negative here than it is here because the weights are getting bigger. Yeah, I think that's what would happen. Yeah. Yeah.
Okay, but you can apply this to something else at deep learning, right? I mean, for instance, as you just say, probably, people care about factorizing tensors.
Yeah.
So in this case,
Yeah. I mean, we could collaborate on applying these methods to, you know, or you could just do it yourself. I mean, it's just any new method for descending the landscape gives you new information, right? And comparing how different methods descend the landscape gives you more high resolution information about the landscape. But I mean, the practical algorithms for doing matrix factorization are very different from gradient descent, right? There's these alternating minimizations and this and that. So I don't think this would yield a.
I guess it depends on the regime, right? I mean, it depends on the size of the system. And
Yeah.
so many people would still advocate to gradient descent for problems which are known.
Yeah, gradient descent, stochastic gradient descent is a workhorse, right? It works on everything, right? It's really nice that way. But if you have special structure in the problem, you often get an advantage from being more sophisticated. Okay, excellent. All right. Now I want to show you some fun movies that involve non-equilibrium thermodynamics. So, yeah.
Is there data to support the idea that the lowest minima are bad for generalization?
Yes, there is. There's this picture that's emerging, and who knows if it's true or not, but there's some preliminary simulation evidence that let's say you have a very sharp deep minima, but a shallow higher minima in the training error, right? Now remember, the training error is the wrong function to solve. You want to solve the generalization error, right, or minimize the generalization error. But they suggest that if you find this valley, then you will generalize better than if you find this valley, because if you shift to generalization error, what might happen is the generalization error function will be a slightly different function, right? Okay, but you found the minima here, but in terms of generalization error, it's over here. Whereas here, because you're very robust, right, if you find the minimum here, the generalization error will be, well, it's going to be higher. Sorry, generalization error is always higher than training error. And you know it'll be here, right? So there's kind of a mantra out there that a bad optimizer is a good generalizer, and that might actually be true. If you Google like deep versus flat minima, you'll find the relevant papers. I don't have them off the top of my head at the moment. Again, theory for that is completely missing. All right. Okay, I wanted to shift to some fun videos and discuss. There's another aspect of deep learning which is called generative modeling. Right. This is asking deep networks to really understand the statistical structure of the world, and this is really going to unsupervised learning. So you may have seen these things where like deep networks can generate images of new bedrooms that it's never seen before, or new images that it's never seen before. So kind of early on, we had some work where we were trying to generate very deep generative models, actually using ideas from non-equilibrium thermodynamics. So it's kind of fun, I think, for this group. So the basic idea is, we want to learn complex probabilistic, and this is work kind of led by my postdoc at the time, Joshua, who's now at Google, at Google Brain. So we want to learn a probabilistic model of the world. The problem is there's a trade-off between the simplicity of the model, or the flexibility of the model, and how easy it is to learn the model, right? So we can all learn a Gaussian by a second moment method, mean and covariance. But a Gaussian can't express complicated distributions. They're very, very complicated distributions, but they're very hard to train. We would like something here, a complicated distribution that's easy to train. Okay, how might we get there? There's lots of ideas. Yeah, that's where we want to get. There's lots of ideas in the field, but we tried out the following idea. Okay, this was actually motivated by the Jarzynski equality and basically short violations of the second law of thermodynamics and short timescales, quote-unquote violations, where entropy can transiently decrease for small systems for short timescales. So basically, you could potentially create structure out of noise. Okay? But the basic idea is we don't want to create any old structure. We want to create structure in the training data. So the basic idea was let's destroy structure in the training data through a diffusive process. Okay? So we create a diffusive movie that destroys your data. We carefully record that destruction of structure, and then we train a deep neural network to reverse time to create structure from noise. Okay? And again, it was inspired by these recent results in relatively recent results in non-equilibrium thermodynamics. So again, the picture is, let's say you have a complicated data distribution represented by this die. Okay, you let the data, so each die particle is one data point in the space. And you let it diffuse, so it becomes a simpler distribution. Right here, it will become uniform. We know how to sample from a uniform distribution. Okay? We don't know how to sample from the distribution that represented the die directly. But now what we can do is we can look at the trajectories, and then we can create a generative model, a probability distribution, in the following operational sense. We sample from the uniform distribution, and we run the dynamics backwards to generate the die, the original die distribution. Okay? But of course, we don't run diffusion backwards. We train a neural network to reverse the diffusion. Okay? So that's this idea. Okay? So how does it work? So let me give you, and I will switch to the movies. So we've come a long way since the BPP transition. All right. So here's kind of a let's first apply it to a toy model, right? So this is a toy, this is called the Swiss roll. In machine learning, that's a toy complicated data distribution, right? And so these are data points. Now we're going to have every single data point diffuse independently, so just normal diffusion in a quadratic well, right? That's an Ornstein-Uhlenbeck process. Its stationary distribution is a Gaussian. So if we run that forward in time, you see just what diffusion does, right? Okay. But now what we do is we record for every data point its trajectory, right? So we have a movie with a sequence of time frames. If the movie runs this, no, you guys are looking, let's say the movie runs this way, right? We're going to train a neural network that has a layer, one layer for each time frame, right? And the weights between successive layers have a very simple drop. Reverse the movie by one time frame, right? So it's basically reverses that structure, right?
So it's super deep.
Super deep, 1,000 layers, right? but we're circumventing the credit assignment problem. We never have to backpropagate because we're providing targets at every single layer, because we only have to reverse the movie one time step, and we know what happened in the past of the movie. So the past of the movie becomes a training target for the future of the network or the next layer of the network. Okay? So if it works, I should be able to input random Gaussian noise into the first layer and run the network forward, and out will pop the Swiss roll. Okay? Now I'm going to show you the propagation of activity through the neural network as a movie, but now you're running time as if you're going forward in the layers of the trained neural network, and this is what happens. Right? A Swiss roll pops out of the noise. Okay? What this system has effectively learned is it's learned a time-dependent vector field that starts from anywhere and directs you to the Swiss roll. Okay? All right, let's do something a bit more complicated.
Do you have to train it on multiple Swiss rolls?
No. I mean, you need multiple data points, but all of the data points are here. So you saw the entire training set in that movie. Okay? Yeah? Yeah. We have access to all the time slices of the movie. If we didn't, we couldn't do this, right?
So here, this is fascinating. So we have Markov processes.
Yeah.
Went to equilibrium. That's
Yeah.
Einsteinian, but
Yeah.
you have different ways. You can go softly, like a movie.
Yeah.
And then you can go back, or you can have a cutoff phenomenon.
Yes. Yeah. Non-normal.
I guess when you go,
Yeah.
it must be super hard to do.
Yeah, I agree. I don't believe that diffusion in a quadratic well has that non-normal cutoff, right? You're right, but if we had the non-normal cutoff, we'd be in trouble. If I remember, diffusion on the hypercube does have that cutoff, right? Yeah.
So if on the hypercube you started from a pattern.
Yes. Yeah, that's exactly right. Though we did do this for binary data, and it worked, so I'm not sure how that relates to that. By the way, there's an interesting thing. We changed the diffusion constant dynamically so that we maintain information about the past, which is what is used by the neural network to reverse the flow of time. Yeah? Oh, yeah, that's in the training data. Yeah.
How do you know the network actually learned the dynamics instead of the original pattern?
Oh, we plotted, yeah, I don't have it here. It's in the paper, but we plotted the vector field. And we see that the vector field is directing every place towards the Swiss roll.
Have you tried the generalization error on this? You take
Yeah,
the Swiss roll, you move it a bit, and you see if you...
Oh, it will shift the Swiss roll back to the Swiss roll it was trained on. Yeah, that's what will happen, yeah, based on the vector field. We'll always output this Swiss roll, because that's what it was trained to do, yeah. Uh-huh. Yeah. We'll move to more complicated ones soon, yeah. By the way, your question about generalization, the right way to ask it is the following. Let's say I give you a data set to the Swiss roll, but I don't give you any data points here, okay? Then I take the data points that I do give you, and I figure out where they went, and I kind of interpolate between them, and I run it backwards. Do I end up in a vicinity where I had no data? That's the right generalization question that you asked. We haven't tried that, actually. We should look at that. But based on the more complicated things, we see interesting generalization, which I'll show you next. So, so we next tried this in a slightly more complicated data set. It's a toy model for the statistics of natural images. Remember, we talked about yesterday, natural image statistics is still an unsolved problem. There are many models out there, but none of them capture the entire structure of natural images. This is a toy model where you just throw down leaves, in this case circles, of different colors onto the screen, and they occlude each other. The distribution of radii of the circles have a power law distribution matching the scale-free structure of natural images. You get these homogeneous regions, and you also get sharp edges. And moreover, you get angular correlations in the edge orientations as you move along the image. So that's the kind of stuff this captures about the low-level statistical structure of natural scenes. So then we trained so then what we did is we took a whole bunch of dead leaves images, and we just had each pixel diffuse in intensity space independently of every other pixel. So that's the diffusion process that destroys structure and data. we had these movies that turned dead leaves into white noise. And then we trained a neural network on these multiple movies to reverse the flow of time in this destructive process. If it works, you should be able to feed a white noise image into the first layer, run it through, and get out an approximation of a dead leaf image. Okay? So let's try that. So let's run. So this is what the trained network does. Wow. Oh, there it is. Okay. Okay, so it creates the approximation. So it gets a lot of things right, but of course not everything. It does get like a roughly scale-free distribution of homogeneous regions, right? It also gets the sharp edges. It's difficult to get both homogeneous regions and sharp edges together. It also gets angular correlations in the orientations of the edges, sort of, at least at a qualitative level. The next best model was this one, and as you can see, we're kind of qualitatively doing better than them. And if you actually compute the log probability of real dead leaves images under our probability model, we see that we also do quantitatively better. Okay, now can you use this for something useful? And the answer is yes. The whole reason behind having generative models that really understand the structure of the data set is that you can now ask conditional questions, right? If I have some part of the data and some other part of the data got knocked up, or not knocked up, but destroyed or corrupted, then can you kind of fix it, right? So here's an example where you, by the way, we also tried this on natural textures, like many, many images of bark, right? And it kind of generated random images of bark. And what we did is we turned the center of the bark into noise. We conditioned the pixels on the outside, and then we fed this image through the neural network. So we didn't allow the pixels on the outside to change. So then information from the boundary should propagate into the interior, right? This is holography. Okay, bad joke. And then it should fill in its best guess as to what it thinks the missing bark is looking like, right? So this is what happens. Okay, and it looks like a relatively reasonable image. Now this goes back to your question about generalization. Is it just so first of all, this piece of bark was never in the training data. So it's a new piece of bark it's never seen before. Okay? But you can compare it. Where did my okay. You can compare it to the actual piece of bark, and you see that it let's see. Oh, it runs in here. Okay, so it doesn't always run in here. So you'll see that the actual piece of bark is, of course, different from what it fills in, right? This does look qualitatively a little bit better, of course, right? But basically, it's imagining something that was not in your training data or not even in the actual sample that was. So obviously, there's probably multiple ways to fill in the interior in ways that are consistent with the entire statistical structure of bark, because it's a pretty big area that we cut out. Okay, so that's an example of like kind of reversing the flow of time using neural networks to learn structure and data, which is kind of fun. And there's more details in the paper and so on. Okay, so, oh wow, okay, I'm 6 minutes over. So that's okay. You know what, I'll just, in 1 minute, I'll tell you what was going on here. Why does a deep neural network express more complicated functions than a shallow one? What we could show is that if the weights are slightly larger, you get this chaotic dynamics that propagates through the network. And it can create highly, highly complicated functions whose curvature grows exponentially with depth. Right? So this is an image of a circle propagating through the network. And in the chaotic phase where the weights are large, you get extremely complicated functions. We can compute the curvature of these functions analytically using mean field theory, and there's a beautiful match between so these are mean field equations for the propagation of curvature. There's a match between the equations and the numerics, a very nice match. And what we can basically show is that neural networks, by basically expanding and folding, expansion through the large weights and folding through the nonlinearity, can create images that are exponentially large in length and have exponential growth in their global curvature, right? But no shallow network can ever do that. We prove a worst case theorem where the corresponding quantities grow only as fast as the square root of the width. Okay? I never told you, but we were looking at the propagation of curvature through random neural networks. So random deep networks can create exponential curvature in a way that no shallow network whatsoever can do better than the square root of the width. So there's a very different character to deep propagation and shallow propagation, even if you have the same number of parameters. Okay? And yeah, just that's it. I'll stop. This is a summary of the part we didn't cover. Okay? Any questions?